Hi, everybody. Today we're going to be talking about something called odds. The odds of an event occurring or the odds against an event occurring. And we'll start out defining the odds against an event E occurring. And we define it this way. The odds against an event E occurring are defined as follows. The odds against E, the probability that E does not occur, divided by the probability that E does occur. Let's see. I'm not a gambler, so I'm not real familiar with odds and things like that. But in everyday conversation, we do hear statements involving the odds for or the odds against something happening. For example, the odds against a person getting struck by lightning in their lifetime is 1,000,000 to 1, or thereabouts. Now, what that really means is the probability of their not getting struck by lightning, which is not E, divided by the probability that they do get struck by lightning, is 1,000,000 over 1. Or another way of putting this, in a person's lifetime, they're 1,000,000 times more likely not to get struck by lightning than they are to get struck by lightning. The odds against a person being in a fatal automobile accident, the odds against that may be 15 to 2, something like that. They're 15 times more likely not to die in a fatal car crash as they are to die in a fatal car crash. As a matter of fact, maybe I should be writing some of these down, just so that we get a feel for what this really means. Okay, let's get to the nuts and bolts of some of these hypothetical problems and use some real-world statistics to work with. Suppose E is the event of getting struck by lightning during a person's lifetime. E is the event that a particular person gets struck by lightning during their lifetime. It turns out, and these are real statistics, the odds against a person getting struck by lightning, 15,300 to 1. Now, I found that kind of shocking. I would have thought it would have been closer to 1,000,000 to 1 than 15,300 to 1. But apparently, and these are real statistics, the odds against a person getting struck by lightning, only 15,300 to 1. I guess the next time I'm outside during a thunderstorm, I better seek cover. Now, let's see where they got this figure, okay? Here's the information that apparently they had to start off with. E is the event of getting struck by lightning. And it seems that they knew that the probability of getting struck by lightning was 1 over 15,301. The probability of getting struck by lightning, 1 over 15,300 to 1, 301. And again, I don't feel too good about this. I'd feel a lot better if this were 1 over 1,000,000 or something like that. But this is apparently the actual probability. The probability of getting struck by lightning, 1 over 15,301. So, what about the probability of not getting struck by lightning? Well, that's going to be 1 minus the probability that a person does get struck by lightning. And what does that work out to? That's 1 minus 1 over 15,301. And to do this, well, we got to get a common denominator, right? 1 is the same as 15,301 over 15,301. So this is just 1. So we have 1 minus 1 over 15,301. We got a common denominator. We keep that common denominator. And we just subtract numerators. 15,301 minus 1, 15,300. So what we've established here is the probability of E not occurring, that is the probability we don't get struck by lightning, is 15,300 over 15,301. Now, let's take these two figures and calculate the odds against getting struck by lightning. Okay? Okay, just a reminder, E is the event that a person gets struck by lightning. The probability that a person gets struck by lightning is 1 over 15,301. The probability that a person does not get struck by lightning, 15,300 over 15,301. These are things we just computed. Now, from this information, how did they get the odds against E? The odds, there used to be an S in the word against. I guess this is the new modern spelling. The odds against getting struck by lightning. And we know that this is the probability that E does not occur over the probability that P does occur. The probability of not getting struck by lightning over the probability of getting struck by lightning. Okay, probability of not E, 15,300 over 15,301. That's the probability of not E. The probability of E, 1 over 15,301. We're dividing a fraction by a fraction. So what do? Don't we take this fraction in the denominator and pull the old invert and multiply trick? Yeah, we sure do. So we take this fraction, the numerator, just keep it 15,300 over 15,301. We keep the numerator. And we take this denominator and we flip the son of a gun. 15,301 over 1. And holy moly, we do get some canceling, thank goodness, because this was looking pretty ugly. And we get 15,300 over 1. Well, we divide anything by 1, that's just the number itself. 15,300. The odds against E, the odds against being struck by lightning, 15,300. That's how they came up with those statistics. You know, I ride my bike out in the rain, and I thought the odds against hitting by lightning have to be at least 1,000,000 to 1. I think from now on I'm going to stay inside when it rains. Now let's look at another example. Here's another one of those real-world examples. The odds against a person dying in a car wreck are 107 to 1. You'll have to forgive me. I went to the Yogi Berra School of Grammar. The odds against a person dying in a car wreck are 107 to 1. And I'm kind of shocked by this. I would have thought that the odds against that happening would have been like 15 to 2 or something like that. I would have thought, something like 2 out of every 15 people die in auto accidents during their lifetime. Not so. Essentially, this is saying approximately 1 out of every 107 people die from an automobile accident, which is not nearly as great as I would have thought. Now, that doesn't mean we shouldn't be careful. And that doesn't mean that just because a person doesn't die in an auto accident doesn't mean they can't be severely injured in an auto accident either. So let's not let this lull us into a false sense of security. But let's see how they came out with these odds, okay? And we'll let E be the event that a person dies in an automobile wreck. And apparently, they had this information. They had the information due to statistics that the probability that a person will die in an automobile wreck during their lifetime, these are lifetime statistics for the U.S., the probability that a person will die in an automobile wreck in their lifetime is apparently 1 over 180 or very close to that. So what about the probability that a person dies from some other cause? The probability a person doesn't die in an automobile wreck, that's going to be 1 minus the probability that they do die in an automobile wreck. And so that's going to be 1 minus 1 over 108. And you know the drill. We have to get a common denominator. So 1 is the same as 108 over 108. So we have 1 minus 1 over 108. We got a common denominator. We'll keep that common denominator. And we'll subtract the numerator. So 108 minus 1, 107. So we've just discovered that the probability that a person in the U.S. will not die in a car accident during their lifetime is 107 over 108. That's the probability. Now, how did they get this? The odds against a person dying in a car wreck are 107 to 1. Let's check this out. Recapping the work that we just did, we found out the probability of E, a person dying in an auto wreck sometime during their lifetime, the probability of E is 1 over 108. The probability of not E, the probability that a person doesn't die in an automobile wreck during their lifetime, 107 over 108. Now, let's use this information to see how they got the odds of a person dying in a car wreck being 107 over 1, or 107. The odds against E occurring, that's the probability that E does not occur, over the probability that E does occur. And the probability that E does not occur is 107 over 108. The probability that E does occur, that's 1 over 108. Look here. We got a fraction divided by a fraction. So what do? We keep the numerator. We keep the numerator. And we take the denominator and we invert it. We flip the son of a gun. So we're going to get 108 over 1. And oh, things are looking good. Things are canceling so well. The 108s cancel. And we get 107 over 1. The odds against E happening, the odds against a person dying in an automobile accident, 107 over 101. And Some people may just say 107, since this reduces to a whole number. Everybody, we're going to turn the tables a little bit now and compute the odds in favor of an event occurring. Up to this point, we've been computing the odds against the odds against an event occurring. Now we're going to compute the odds in favor of an event occurring. And the way we compute the odds in favor of an event occurring, we take the probability that the event does occur and divide it by the probability that the event does not occur. Let's see, do we have any statistics that might be of interest? Odds in favor of winning Super Bowl. This next coming Super Bowl, let's see. How do you spell Chiefs? I guess E before I here. No, that isn't right, is it? Well, I'm sticking with it. Chiefs, the odds in favor of them winning the Super Bowl, 2 out of 15, not bad. Bills, odds of them winning the Super Bowl, 2 out of 15, not bad. Who won the Super Bowl last year? I think it was the Rams. What do the prognosticators think of the Rams this season? The odds in favor of them winning the Super Bowl, 1 out of 11. Man. What about the Patriots? Come on, Patriots. Oops. The forecasters don't think too much of the Patriots winning. The odds in favor of the Patriots winning, 1 out of 22. Oops. These are the two front runners right here. Not bad. And the Rams won last year. The odds in favor of them repeating, 1 in 11. Well, I guess maybe part of that has to do with the fact that it's really hard for a team to repeat. These guys, they had a good team. They still have a good team. But even for a good team, it's really hard to repeat. So I think this is what drops them down to 1 over 11. Now, let's use some examples where we can actually apply this formula, okay? Here's an example involving odds that's sort of different than what we've been working with so far. A single card is drawn from a deck of 52 playing cards. And the event that we're interested in is the event of drawing a face card. And we want to compute the odds in favor of drawing a face card. The odds in favor of the event E occurring. In order to do this, we need to know the probability that E occurs and the probability that E does not occur. So let's do the probability that E occurs. And notice that we're picking one card. There are 52 cards in a deck, so there are 52 possible outcomes. And the deck's shuffled real good. Every one of those cards is equally likely to be chosen. So each of these outcomes is equally likely. The probability that E occurs is the number of ways that E can occur divided by the total number of outcomes. Another way of saying this, the number of outcomes that result in E the number of outcomes resulting in E over the total number of outcomes. Well, let's see. Compute the odds of drawing a face card, and we'll define the rules. Face card, for our purposes, is going to be Jack, Queen, and King. Some people say that aces are a face card. For the sake of this example, we'll restrict face cards to Jacks, Queens, and Kings. Now, how many outcomes result in a face card? Well, let's say Jack of clubs, Queen of clubs, King of clubs. That's all the clubs. Let's see. Then there's clubs, diamonds, okay. Then there's Jack of diamonds, Queen of diamonds, King of diamonds, clubs, diamonds, hearts, Jack of hearts, Queen of hearts, King of hearts, and we have left spades. Jack of spades. Is that what a spade looks like? Maybe I'm drawing it upside down. Jack of spades. Nah, I think it's the other way around. Jack of spades. Queen of spades. King of spades. Those are all the ways that we can get a face card. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 ways of getting a face card. The probability of E getting a face card, number of ways E can occur, or a number of outcomes resulting in E, over total number of outcomes. ways E can occur. And how many outcomes total are there? There are 52 cards in the deck. Each one of those is equally likely. And I think we can divide top and bottom by 4. Okay. Probability that E occurs is 3 over 13. Now, to find the odds in favor of E occurring, we also have to find the probability that E doesn't occur. We need that. Whoops. Let me be thorough here. The probability that E does not occur is 1 minus the probability that E does occur. And that's 1 minus 3/13. We get a common denominator here. 1 is the same as 13 over 13. So we have 1 minus 3 over 13. And that's 10 over 13. The probability of not E equals 10 over 13. Okay. Now I'm going to erase some of the board. Recall that the event that we're looking for is selecting a face card from a deck of 52 playing cards. So E is the event that we draw a face card. The probability of E occurring is 3 over 13. The probability that E does not occur is 10 over 13. And the odds in favor of E occurring, let's see, how do we do that? You remember? Isn't it the probability that E does occur over the probability that E does not occur? That's what it is. And so we get 3 over 13 over 10 over 13. A fraction, a quotient where the numerator and denominator are both fractions. We're going to keep the numerator, and we're going to take the denominator, flip it. We're going to invert the denominator and multiply. And those 13s, they cancel. The odds in favor of drawing a face card, 3 out of 10. Not bad odds, but not good odds either. Certainly less than 50%. Well, let's try another one. Let's try another one. Hey everybody, we got another goodie. A single die is thrown once. What's a die? If we have a pair of them, we call them dice. Or if we have more than one die, we call them dice. So a die is just one of these six-sided cubes. The event that we're looking for is the event that the number that's face up on the die is greater than 4. And we want to compute the odds in favor of E. And to do this, we need to know the probability that E occurs and the probability that E does not occur. And notice, all of the outcomes of this experiment are equally likely. We toss a single die, we can either get a 1, 2, 3, 4, 5, or a 6. They're all equally likely. So the probability that E occurs is the number of ways E can occur over total number of outcomes. And that's the same thing as saying the number of outcomes that result in E over the total number of outcomes. The total number of ways that E can occur, or the total number of outcomes that result in E. How is it that if we toss a single die, we can get a number that's greater than 4? Well, we either get a 5 or we get a 6, right? So there are two ways that E can occur. And the total number of outcomes, there are 6 numbers on the die, 1, 2, 3, 4, 5, 6. So there are 6 total outcomes. And that reduces to 1/3. The probability that E can occur is 1/3. And the probability that E does not occur, that's 1 minus the probability that E does occur. And that's equal to 1 minus 1/3. And we get our common denominators here. 1 is the same as 3/3. So the probability that E does not occur is 2/3. Okay, let me clean up this board and we will be back in business. But just a reminder, E is the event that we toss a single die and get a number greater than 4. That probability is 1/3. The probability that E does not occur is 2/3. And we want the probability, no we don't, we want the odds in favor of E occurring. So that's going to be probability that E does occur over the probability that E does not occur. Probability that E occurs, 1/3. Probability that E does not occur, 2/3. We have a quotient of fractions. We keep the numerator, and we take that denominator and invert it and multiply. We flip the son of a gun. And the odds in favor of E, 1-2. We've done a few examples, and in each of the examples we've done, odds against an event happening, odds in favor of an event happening, there's always some canceling going on. We always have a quotient of fractions, and we keep the numerator, and we flip the denominator, and then multiply. And there's some canceling. And if we look back at each of the examples, the number that gets canceled in each case is the total number of outcomes. That's always going to cancel if we're doing an experiment where all of the outcomes are equally likely. As a consequence of this, the formulas that we have been using can be simplified. And in a case where all outcomes are equally likely, the formulas can be simplified. Now, I will say this, the formulas that I'm about to show you, they're simplified. They don't apply in all situations. They only apply when all outcomes are equally likely. You can get by and do all of the exercises in our book without using the simplified formulas that I showed. So if you're satisfied with the formulas that we've been using, you don't need to know this. I will show you this. It only applies in cases where we know that that the outcomes are equally likely, and where we know the number of outcomes in favor of an event occurring and the number of outcomes against. Let me say that again. It only applies when we know the number of outcomes that result in E occurring and the number of outcomes that result in E not occurring. And sometimes when we do problems involving odds, we don't know this. We don't know the number of outcomes in favor of something happening and the number of outcomes resulting in an event not happening. For example, the number of people who in their lifetime die in an automobile accident. We don't know the number of outcomes that result in E. We don't know the number of outcomes that don't result in E. The odds against a person getting hit by lightning. We don't know the number of outcomes that result in a person not getting hit by lightning. We don't know the number of outcomes resulting in a person getting hit by lightning. So in cases like that, the formulas that I'm going to show you don't even apply anyway. The formulas that I'm about to show you only apply in situations where all outcomes of an experiment are equally likely, and we know how many of those outcomes result in the event E occurring, and we know how many of those outcomes result in the event E not occurring. And here are the formulas. Odds against E. Number of outcomes resulting in E over, whoops, I was about to do something wrong, forgive me, over number of outcomes not resulting in E. That's the odds against an event E happening. Similarly, the odds in favor of E oh my goodness, I screwed up already. The odds against E happening, forgive me, the number of outcomes not resulting in E over the number of outcomes resulting in E. I apologize. The odds against E happening, the number of outcomes not resulting in E goes on top. The number of outcomes resulting in E goes on the bottom. The odds in favor of E, we just take this and flip it. Number of outcomes resulting in E all over the number of outcomes not resulting in E. These are a little bit easier to use when they apply. These formulas don't always apply. So if we're satisfied using the formulas that we already have, those formulas always work, and we don't need to use these formulas. I'll show you the formulas anyway. I'll use each one of these in an example. Maybe some of the examples we've already done. But these formulas only apply where all outcomes are equally likely, and we know the number of outcomes that result in E, and we know the number of outcomes that don't result in E. Okay, let's apply these formulas. Here's our first example. A single die is thrown once. Ooh, where have we seen this before? Compute the odds in favor of the number that's face up being greater than 4. Essentially the same example that we just did. E is the event that the number that's face up is greater than 4. Odds in favor of E and you remember what that was? Well, let's stop for a minute. Are all of the outcomes of this experiment equally likely? We toss a single die. There are 6 outcomes, 1, 2, 3, 4, 5, 6. And all of them are equally likely. Okay, I guess that works. The odds in favor of E occurring turn out to be the number of outcomes resulting in E over the number of outcomes not resulting in E. How many outcomes result in getting a number greater than 4? Just 2, right? We can either get a 5 or a 6. There are 2 ways that we can get a number greater than 4. So the number of outcomes resulting in E are 2. How many outcomes don't result in a number greater than 4? 4 of them, right? 1, 2, 3, 4. All of these are, none of these are greater than 4. So the outcomes that don't result in E are 1, 2, 3, 4. There are 4 ways that E can fail to occur. We used our new formula. We got the same answer that we got before. Now maybe we'll do one where we're looking for the odds against E. Slight variation on a familiar theme. A single die is thrown once. Compute the odds against the number that is face up being a 6. So the event here is that the face up number is a 6. And we want the odds against the event E occurring. The odds against E occurring, number of outcomes, the number of outcomes not resulting in E, over number of outcomes resulting in E. E is the event that the face-up number is a 6. There's one outcome resulting in getting a 6. We get a 6. So there's one outcome that gives us a 6. How many outcomes don't result in getting a 6? 5. If we don't get a 6, we either get a 1, a 2, a 3, a 4, or a 5. So the odds against E occurring, 5 to 1, or we might just say 5. Now note that we could have used our other formula here. We could have used probability of not E over probability of E, and we would have gotten exactly the same thing. As a matter of fact, this formula and the formula in favor of E, which is probability of E over probability of not E, these two, and I might as well just be thorough. This is odds against, odds in favor of. These two formulas always work. The formula that we used here works when we know the number of outcomes that don't result in E and we know the number of outcomes that do result in E. It's a simpler formula, but we may not always have these two pieces of information. Just a footnote here. Our authors say that at gambling venues, people are provided with the odds. They're provided with the odds, but they're not told if the odds are for, in favor, or against. They're just given the odds. They're not saying the odds in favor of, they're not saying the odds against. At a gambling venue, they're just given the odds. And our authors want us to know that if we're in that environment and we're given the odds in a gambling establishment or that environment, these odds typically are the odds against something happening. So if we're given the odds in a gambling environment or something like that, typically they're talking about the odds against an event E occurring. And I don't think there are any exercises in the book that require us to make that distinction. I think the exercises all explicitly either say in favor of or against. I think the authors just told us that so that if we do find ourselves in that environment, we don't make the assumption that when we're given the odds, we're being given the odds in favor of something happening. In a gambling environment, we're being given the odds against something happening. And just my own personal view of that, I don't go to those places. Those places make money, but they can't make money unless, on average, the people who go there lose. And it's highly unlikely that we're going to be somebody who wins big. And if we do win big, the people who run that place may not really appreciate the fact that we've run big, that we've won big. And they may, depending on the establishment, do something to make sure that we don't enjoy what we won. So don't go to these places, please, and think that we're going to outsmart the people there with a system that we got worked out. It's highly unlikely that that's going to happen. These places don't make money unless, on average, people who go there lose long term. And believe it or not, places like this hire experts in probability and statistics to make sure that the house wins over the long haul. So just my own personal viewpoint, I think I'm a pretty smart guy, but I think that a genuinely smart person probably won't go there because they know that a person over the long haul is going to lose rather than win. And I think if we spend our money elsewhere, that we may be able to enjoy it. I think Ecclesiastes 2:24 says something to the effect, there is nothing better than for a man or a woman to eat and drink and see good for all their hard work. If we work hard and we achieve something, that's when we can truly enjoy it. If we haven't worked hard for something and we get it, chances are we're not going to enjoy it anyway. But just as a disclaimer, our authors have told us typically what is meant if we're in a gambling establishment, we're given the odds, we're being given the odds against something happening. And for those of you that are inclined, well, at least you can take that tidbit of information and